My name is Jean-Philippe Paiement. I've been, like my colleague, I've been consulting for most of my career, which is much younger. I was 10 years in. And mostly for SGS. I worked for tech a little bit before the American crisis, but that didn't last. So yeah, well, what I wanted to present today is not really how we won the challenge, but how and what we integrated into our submission that was kind of new, not used predominantly in the industry. But really greatly introduced by Mo. So you're all good in conditional simulation now, so I'll be able to talk about it and you guys all understand. But basically, yeah, so we combined geostatistics, machine learning, and Oculus Rift technology, so virtual reality, to produce something that was innovative, I guess. Let's just move through quickly. So again, like Nathan said, we won the Gold Rush last spring. It was a team effort from myself, my manager, Guy, Doug Atfield, which is one of our Met guy, and the machine learning guy for this thing, and the whole team, actually. Since it was kind of a downturn last fall, everybody pitched in, and it turned out a great profit, actually. So yeah, so just a little cautionary statement, like everywhere, we're not selling the Integra. We're not also, the goal is not to sell ourselves, but mostly to show you what's new out there and what we've been doing for the past year. So since we won, actually, we've worked on developing other type of projects like this, but also new types of modeling and estimation. So I'll talk about that a bit later. So just a quick introduction to the company, but we used to be Système Geostats International. We got bought by the great SGS family 7 years ago. And we have pretty much a worldwide footprint as of project experience. So we worked in all kind of different environments. The main office is still located in Blainville, which is north of Montreal. I am in Quebec City with the ever-growing office of 2 people. Yeah. So basically our approach for the Gold Rush Challenge was to produce a targeting method that used all of the data, so a big data bunch, to produce the less drilling possible and find a more gold possible. That was kind of our selling pitch. But mostly what it says is it says that we were trying to get all of the data fed in and used to better target mineral target and mineralization. So the approach we had is a common approach that's been used in the industry for a long time. It's just to get all the data into a matrix. So the space was divided in equal size cube, and all the cubes were informed according to different variables. The variables we chosen were the vectors towards mineralization that had been identified in the mining camp a long time ago. But what separates us from the other guys is that instead of just scoring the block using geological knowledge here, which is commonly known as weight of evidence, we also submitted the entire thing to a machine learning algorithm to see if it could find any correlations between data that we couldn't see as a geo. Most human, well, all of you guys can see correlation between 2 variables, maybe 3 if you're really good, but past that, it becomes hard to see because we have just 3 visual dimension. The machine learning is really good at finding correlation between X set of variable, which is something that actually happens in geology. It's not one factor that contributes to ore forming. It's a combination of different parameters of specific space. So we use that to rate all of the blocks that were oh God, you guys all know what I'm up to. To rate all of the blocks that were in the model according to a prospectivity score, which is a number between 0 and 100. So 100 is a target, 0 is no target. So anything between 100 and 0 would be classified. And then what we did is we pushed the blocks, we queried them to create volumes, and we used the virtual reality just to see if it aligned itself properly with the structure that were identified in the mining camp. So I don't know if you're aware of or know about the Sigma Lamaque mine, but it's a huge history. There's lots of work, lots of papers have been published on that mine. So the structures, everything is really well known, really well mapped. So we were able, using the Oculus Rift, to actually identify structures, see if our targets were within the structural continuity of other targets, and stuff like that. So, and in a big data set like that, it really helped actually, because we could blow up the model to the size of the room here and actually walk around it instead of just spinning the 3D model in a small screen. So that's something that's really becoming helpful for us. So we'll go a bit on the science of things. I'll explain what we did and what was new and how we brought everything to the matrix. So the goal was to use all of the data and push it into the block model that we use to generate the targets. So the first step, the deposit is a structurally controlled deposit, so there was some structural work needed to be done. It was not much structural measurement in the Integra database, but fortunately it's in Quebec, and we have quite a good government database that's publicly available, that's free, so you can download everything from there. So we went and fetched data from the government. Lots of structural mapping has been done by different geos in the area, so we were able to build a little structural model. The reason we wanted to do that is that there's different structures that control the mineralization differently. In that case particularly, we're looking for the third order faults, which are environment that are brittle fracturing and mostly an extension within the compressive regime. If you look at the first order fault, which is this is the Cadillac Trust, is mostly compressive. It's a good fluid pathway, but it's not really good to deposit gold. So you need an extensive environment somewhere to open fractures and circulate a lot of fluids. So we're looking for third order faults. Using our structural interpretation, we were able to find the directions and dip of these faults. So what we did is we used the database from the government, the MAG we had, and we were able to map the different type of faults. So here's the mapping of the first order faults with their measurements. These are the second order faults, and these are the third order faults. So with that, we're able to build a 3D model of the faulting around the property. So that's the first step. That's something that everybody does. But now, what we wanted is not exactly to know if a block was located or if a fault crossed one of our block, but we also wanted to know at what distance the different blocks were, because it's not really on the fault. The fault must be might have some interpretation errors too. So what we really want to see in our model was the distance to each of the type of faults. So from 3 sets of faults, which are first order, third order, and second order faults, we not only created 3 variables according to if a fault went through the model or not, but we created 6 variables with the distance of each of the faults according to the block. So from that little piece of interpretation, we're able to generate 6 different variables that could be used for machine learning. And you have to keep in mind that machine learning is really good at and really likes having a lot of data to play with. If you feed it 2 or 3 data, it's not as good as if you feed it a lot of data. So now the second step was to build the geological model. So fortunately, we had a really good database for geology that's been drilling there for almost 100 years. So lots of lithos. The problem is a little bit too many lithos. We had to simplify things to get something going. But basically what we identified was intrusive played a really important role just because they fracture a lot easier than the mafic volcanics that were around. So we identify the structural model, so the orientation of the different intrusions, and model them using our software. The other thing that we did is just some basic box plot, see if any of the litho came out as a good gold-bearing litho. So here you see the first intrusive, the dikes, the felsic dikes. The veins are high mineralization, obviously. So we decided on 2 main lithos that we wanted to model, which were the felsic dikes. So this is the leapfrog model resulting of the modeling work we did on the felsic dike. Problem with these models is that they're static. They're deterministic. That means that a block is either in the intrusive or outside of the intrusive. That doesn't take into account the risk on the modeling itself. Modeling 3D solids interpretation does create a risk, and that we needed to address that problem also to be able to generate targets that were ranked as for priority and also according to their risk. So this is the leapfrog model for the diorites, which were the first intrusive to come in. So again, it's a deterministic approach. What we had to do then is use the geostatistics approach, just like my friend told about here, but using the variography and the geostatistic approach, we were able to run simulations on the geology. So instead of simulating grades, like the mining industry is used to do, or some people do. I wouldn't say used to it. What we did is we simulated indicators, so either ones or zeros. So one, your drill hole, that interval of drill hole is the litho you want to model. 0 is not the litho you want to model. So you code all of your composites with ones and zeros, and you're able to run simulations on that. This is the average simulation result for the diorite. So what we did is actually all of the drill holes were coded with their composites with ones and zeros. The hot colors are greater chances of having diorite within this block, and the gray are lower chance. So again, using a variable as simple as litho, which would be yes or no normally, we could add to it a probability of being right. Okay. So what you see here is basically a cross section around here on the property, and you see the different intrusion kind of pop up. This is the Sigma mine. This is the Lamac mine. You see intrusive also elsewhere on the property, which is always a good thing for these kind of targets. Then, so we now have 6, 7, 8, 9, 10 variables in our model, but we wanted to add more information. The other information that was provided within the database was the gold grades themselves. So what we tried to do is actually extrapolate an impact on their proper orientation and planes. Okay, so this is not at all resource estimation. That goes against what we're supposed to do. But what we did is just we extrapolated at large through all the block models using the composites that were good enough. The ellipses we chose for these three interpolation are actually based on the structural measurements of the different veins. So if you see, that's the Sigma model, that's the Lamac model. They're quite complex, and there's actually three major family of veins within the deposit. So what we did is we built 3 different ellipsoids, such ellipsoids in our model that were quite large. Again, the goal was to kind of see what was the extension of those veins. And we ran interpolation on those. So what you see, so this is the fault model. So what you see here is, so this is kind of the wireframes of the veins themselves, and these are the 3 ellipsoids. The first one we did was kind of the main direction, which is vertical east-west direction. So these are all the blocks interpolated using that direction. With the other direction, which is somewhat flat. They call them the flat veins, but they're not really flat. And the third one was a north 69 direction. So these are 3 different variables that we were able to add to our model. The other thing we did is we wanted to know if there was actually gold or known gold in a block. Okay, so if there is drilling in a block, you actually have the information, so you don't have to extrapolate. So what we did is just plain simply, we took weighted average of the different assays within a block and coded the block with a known average grade of that block. So that's a good indicator as well when you're targeting. Next, we fetched some data again on the Ministry website, but we came up with some geochemical data. So another big part of origin gold deposit are alteration patterns. So what we did is try to identify different alteration patterns. So basically we came up with our own in-house alteration pattern for this deposit, but it's basically a ratio on calcium and iron, on sodium, potassium, and magnesium. Basically, as you go close to the vein, the calcium and iron increases and the rest of them decreases, so the ratio changes. We actually did them separately for the different rock types because they don't have the same mass balance to start with. And we came up with a map of the alteration, which is something like that. So that's our proximal alteration index. That's how we called it. It's PEAI. It's also the first 3 letters of my name. Yeah. So that's what we did for that project. But we actually had another client come up with a whole set of data on a similar targeting approach that had 63 elements analyzed and no clear alteration patterns. So what we tried was a bit like what Mo showed on the decision tree they made for the gold and the litho. But what we use is an algorithm that's been used by biologists for quite a few years, but it's called phylogenetic, and that's the algorithm they use to take a whole bunch of DNA data sets and see if there's any slight changes in the DNA data set. So it starts with a common ancestor and actually separates the different DNA sets into different evolution patterns. That's applicable to geology because if you have an alteration pattern on a rock, you start with a common ancestor, which is the rock's composition, and you actually evolve towards different other composition with adding or removal of elements. So that's something we did for another client to create that alteration patterns. It's not yet published really, but if you follow us, you'll be hearing about it the next few years. It also applies really good in the petroleum industry. The other thing we also pushed in our model was quite simply the arsenic content of the rock assays. So there's a good correlation between gold and arsenic in that deposit. So we built that to our 3D model. So as we go, we're increasing the level of data. We're trying to merge as much as data as possible into the model to make sure that we're leveraging everything and every known scientific fact about these kinds of deposits to target them. The next thing we did was taken from the literature, but it's actually a way of mapping if there were fluids circulating in a rock body. So they used, it's work done by Georges Baudouin at Laval University, but using oxygen isotope, you're able to map the fluid to rock ratios from hydrothermal circulation, and you're able to map areas of greater fluid circulation. So that's something we also included in our model. The more fluid that goes through the rocks, the better chance you have of forming economic grade gold deposit. So again, here that's just a cookie cutout of the block model within the high fluid flow zone with the blocks being queried or filtered using the proximal alteration index. So you see that the sigma lambda max comes out as a big bullseye there, which is again a good proof of concept for us. So we're still going on to some more data we had. This is the most important actually for what we wanted to do, but the company not only wanted areas of interest around their mine, but also maybe grassroots areas. So you need to know if there's a drill hole near where you're drilling. So what we did is basically that's quite easy to do, but it's just the distance. Each block is coded to the distance of its nearest sample. So you know in each block if there's a drill hole near or not. So that's something important when you want to prioritize your exploration. The other thing we did, we coded each block according to their distance to the underground workings. Because maybe they wanted targets that are close to underground workings, so it's cheaper to go get them if they actually become ore bodies. So that's something we also built into the model. So these are the results. So all of this was pushed into a single block model. So you're thinking one file with X column. That could be queried, that could be ranked, that could be fed to a learning algorithm. But also that leverages everything that's known about the deposit and all of the data that was available to us. It would have been great if we had a mag inversion. There was a surface mag that we used for structural interpretation, but you can feed it a mag inversion. If you have 3D IP, you can feed it to it. The more data you feed into it, the better it is for the machine learning. So basically what we did, the first step was to create a weight of evidence ranking process. So basically we took a variable, assigned the scoring to it. So for instance here, you're looking at near underground mine targets. So we thought that the targets were better between 0 and 250 meters of a third order fault. So that was 10 points. If there is a first intrusive or a dike, a known presence, that's 40 points, and it goes on to 100. So each target has a maximum value of 100. So the other thing we did is actually put some near underground mine targets, open pit targets, underground targets within areas that were well informed, and underground targets in areas that were poorly informed. So that gives us a sense of risk, and it helps into the business decision. Am I looking for ore to feed into the mill next year, or I'm looking for something down the road? The particular approach of this one is they have a mine, they have a mill, they want to start it, and they want to feed the mill as soon as possible and make sure that they get the throughput that the mill is designed for. So they were interested in those two targets first because they represented more economic values. So basically, if we look at the open pit prospectivity score, So we limited the depth of our model for this one because you can't open pit all the way to the bottom of the earth. But basically, again, the color coding is closer you get to red or pink, the higher probability of having a target is. What reassured us to start with is that the Lamaque and Sigma mine came in as targets, so that's a good proof of concept always. But we also found a zone here. So that's the Sigma Lamaque, that's plug 4. And this is a zone that no data has been provided in the Gold Rush Challenge, but we knew about it. It's called a triangle zone, and this is what Integra has been drilling for the past 6-8 years, and they're starting to mine near future. But no data has been provided for that area in the challenge. The reason is it was Integra's proprietary data, and they only provided the historical data. But it was really cool for us to find the triangle zone within our targeting method. Now moving on, this is the second targets we kind of produced for these guys were the underground proximal targets, so targets that were close to known mines. So again, you see that the extension of plug 4 comes in. There's a few targets within the Sigma Lamaque area, but what came out is actually the Lamaque Deep and Sigma Deep targets. These are 2 targets, and they're actually drilling a 3,000 meter hole right now, trying to reach these guys. Thirdly, what we did is just, again, we filter out the block model, but these are the well-informed areas targets. So again, you see the extension of the known mineralization come out quite nicely. And what we did after that was the poorly informed, so basically less data, less reliable, more risky, but maybe bigger payoff because you're most likely you have a better chance of finding bigger volumes farther away from your known volumes, unless you did a really poor job at exploring firsthand. So basically what we're looking is a cross-section that goes through here. That's the entire model we built. So that was, I think, 800,000 blocks. You see the Sigma Lamaque, plug 4, and the triangle zone I talked about. This one had no data, but it still came out as a really high area. So what we did on the other side is that was a weight of evidence, but we thought about leveraging the data and trying to extract the most of it by using artificial intelligence, again, which is a great way of finding correlation between data sets that you guys can't see or I can't see or anyone can see. It also is a really good way of ranking the risk of your targeting. So the algorithm we are using currently, not the one we use for the challenge, but the one we're using currently, has a goal, besides predicting a factor, has a goal of reducing the empirical risk to the minimum. So they'll reiterate itself until it kind of reach the bottom or the smallest empirical error it can. Okay, so it'll learn on some nodes, test itself on some other nodes, and then find its error, and then reiterate itself till the error doesn't go down anymore. So that's awesome. The other thing that algorithm does is it predicts criteria, so 1s or 0, is there a target or is there no target, and what is the probability and the risk according to that prediction. So this is something that's really good that we'll be able to implement into our block models and we'll be able to use for the higher management, because they not only want exploration target, but they want to know how risky it is and how much money they should spend on it regarding the risk. So that's something we did. But basically, this is the process we used for the Gold Rush Challenge. We moved to, we're not using Bayesian-Gaussian process latent variable modeling anymore. We're using boosting algorithm, which is a different type of algorithm. But this one is pretty much the same thing, combines different parameters and outputs a ore probability map. So it learns into the blocks that were located into stopes. So we know they're economic. So they learn onto those blocks and try to find the same repeating pattern elsewhere on the property. So machine learning has been around for quite a while. It's really good at facial recognition. I don't know if you guys have iPhone, but now it classifies your photo and knows if it's you on the picture, which is kind of freaky. Google also knows where you're going all the time. I know you sit in your car, it tells you it's like 14 minutes to work. Like, how do you know I'm going to work? Well, that's all machine learning, right? It's pattern recognition. It knows where you go every hour and whatnot. So that's what we're trying to do with the mining industry. Machine learning is still early stage, quite early stage in our industry. It's bound to develop itself a lot. The reason is it's really good at predicting. It's really good at predicting its errors. And if you ask a geo about his model, he's always going to say that there's no error in his model. So it's a good way of classifying this risk. The other reason we're trying to push a bit on that is the fact that some of the deposit we are looking at, our core business at SGS is mostly resource estimation. We do targeting, and now that's my office in Quebec does that most of the time. But the other people at the office do mostly resource estimation. And some deposits aren't risky on the grade sides of things. They're risky on the geological interpretation sides of things. So what we're trying to quantify right now is the risk on the geological interpretation. And machine learning is a great way of doing that. So what's cool about machine learning is that it's unbiased. So it doesn't look for model it saw at another mine unless it makes sense. All right? As a geo, you're totally influenced by where you worked and what type of environment you worked in. So if you worked at a certain mine and then go on an exploration at another mine, well, you'll try to replicate the same model you saw elsewhere. And that's kind of a problem with our industry. We have kind of stable model, but since we're investigating data, it's better to start with no hypothesis and look at the data to build a model compared to having the model in our head and trying to make the data fit the known model that we have. So machine learning doesn't do that. It's unbiased. It's multidimensional, so it finds correlation between more than two variables. And it helped us win the Gold Rush Challenge. But mostly what it did is it predicted the prospectivity score, and then we looked at the targets between ours and the machine learning. They matched quite nicely again, so it was a good proof of concept. So if we look at some of the targets we produced, so if we're looking, so that's a map of the property. You have Val d'Or here. This is the two mines, Sigma-Lamaque, Triangle Zone is here. So we're looking at a cross-section like this through our model. And what we see, well, basically the mine come up quite highlighted, which is normal, because that's what we're looking for. But you see that the extensions are really good targets. We also had a target here, which is the extension of a deeper intrusion that comes all the way near surface, but hasn't explored yet. And this is the triangle. No, this is not a triangle zone. This is the extension of the orientation of a triangle zone, and it's a target that's brand new to the company. This is the cross-section that goes through most of the known areas. So again, the deep Lamaque extension is quite good. Plug 4 has been mined a little bit in the past, but the extension of it at depth might be a good idea. Triangle has been developed, but what we found was a really high strike target right beneath the triangle zone that's been mined. Again, none of the data here was available, and we still were able to produce something that was quite nicely. Following the challenge, they gave us the rest of the data to update the model. So we'll see what comes out of it. So what we try to produce is not only a model that fits all of the data to one platform, but it's also a model that's living and breathing in the sense that if you add data to it, it's going to update itself and learn from its mistakes. So machine learning is also good at that. So if we say there's a target somewhere, we drill it, and we miss, well, it's not going to be considered as a miss because it's just more information in the model, and then it's going to update itself and learn why they thought something was there, but there's not. So that's something we like about it, is the much data you feed to it, the better it becomes. What we're moving to is something that's been used in the petroleum industry for a few years now. It's called fast model updating. But basically, they have a model that's updating itself as they drill. So the drilling bit from the petroleum industry spits out a lot of the data as it goes through the different stratas. And they have a platform which updates the model as it goes, which is quite nicely. We're moving there maybe in a few years, but that would be our all-time goal, especially with technology like on-site labs, like on-rig labs that the Reflex has been working on. If I'm looking at core scan, stuff like that, or just downhole, borehole geophysics would be a great thing to add to the fast model updating. So basically, this is kind of the end result of all that work. So we produce a 3D map with targets that you can look in either virtual reality or spinning around on your screen, but you're able to plan drill holes, see if they go through your targets, and test them in 3D. That's a little, I don't know if it's going to play. So that's kind of a vision spinning around, but these were the different targets we produced for the challenge. I think Rob had the chance to walk through it on stage, which was kind of the highlight of my night. But basically, that's the end product we're able to produce using that technique. Whoa, that's not what I wanted to do. So what's next? That contest came with a big check. So we're trying to utilize it as much as possible in R&D. So what we've been working on in the past few months is to treat big data problems. So we've hired a team of university researcher for improving our machine learning algorithm. So we're taking something that's public at the moment. We're trying to tweak it for geology. So that's ongoing right now with Laval University. We're working on developing a research pool in Quebec on the geological modeling side of things. So trying to move away from that deterministic approach where you draw on section, but to move towards something that uses simulation, but not the conditional simulation, but something more like multivariable simulation with training images. So you'd be able to draw a few images of what you think this is geology, and the computer is going to try to create a model that fits the drilling data or the surface data, whatnot, and try to reduce the risk to the minimum. So that's something we're trying. We're also trying to model risk on faults and surface like that. So just generating 1,000 models and seeing where they overlap and where they diverge one from another and creating risk maps like that. So that's what we're working on right now. Another thing that could be really good for the machine learning side of the thing is the hyperspectral core logging images. But they feed in a lot of data besides the visual side of the thing. They produce maps of mineral content for the core. So every meter of core comes with a content of minerals. For plain geo, it'd be easy to filter out and maybe find intervals. But again, if you feed all of the raw information to something that's able to process these kind of correlation, would be even better for interpretation. So, I don't know where we're moving back there. So basically, what we're trying to do is take all of that data that looks really messy and try to optimize it and use it as much as possible to gain as much value to a property as possible. So that's pretty much it.